Now I'd like to introduce our today's speaker. This is Pavan Kumar Manvi. He is project leader at Avantium in the polymer and application development team. Since 2 years, he is working at Avantium, where he focuses on the development of textiles from PEF. Pavan holds a master in textile engineering and a PhD from the Aachen University. With this, I would like to hand over to you, Pavan, and I would suggest to share your screen.
Sure. Thanks a lot for the introduction. So let me share my screen now. So please let me know if you are able to see my screen in the presentation mode.
It's working perfectly.
Thank you. So yeah, so today's topic is to look for the opportunities for PEF into textile applications. So as the title is seen here, polyethylene furanoate, bio-based polyester for textile industry. So before going into the detail of technical perspective, so I would like to introduce the company very shortly, that who the Avantium is. Avantium is actually very much focused on developing the bio-based chemistry. So this is the summary, but if we see that who we exactly are, actually Avantium is a pioneer in the emerging industry of renewable chemistry. So we are using basically the renewable raw materials, and by using the chemistry route, we are developing new building blocks, new polymers and monomers and chemicals, etc. So that we can find a sustainable route to change the chemistry of polymer industry. And our mission is to create the disruptive technologies and to enable the transition from fossil waste to renewable and the circular plastics. So plastic means not only the plastic component, but also all products made of the polymers. And our ambition is to create a fossil-free chemical industry by 2050. So going into a little bit more detail, that what we are actually doing to enable this. So we know that current market is very much dominated by the polymers and the plastics. If we look around us, then rarely there is any circumstances where we can live without plastic. And plastics are so much dominant, and they are in majority produced from the petroleum oil. So this is not sustainable. Actually, we hear a lot of times in the news, in the surrounding, in the discussions, in the one-on-one meetings, that what the negative consequences of plastics are. I do not mean especially the plastics. Plastics are good material, but where are they produced from? If they are produced from the fossil oil, then we know how much, what are the consequences of extracting fossil fuel from the earth and then converting it into how much energy it is costing, and how much CO2 it is emitting, and so on. And at the end, when the plastics material are used and they are discarded and going to the nature, then how many side effects on the negative consequences we are seeing on the earth, on the even in the marine environment, or in the general surrounding, that these non-degradable materials are a huge problem. So what Avantium is actually focusing at. So on the left side, you can see the feedstock. We are using two kinds of feedstock: agricultural crops and the non-food biomass. So agricultural crops, there we have the waste to extract the waste and the byproducts of the crops. And similarly, from the non-food biomass, such as from the forestry, etc., we can also use as a raw material, and we convert them into sugars. And these sugars are actually the clean raw material for production or the synthesis of FDCA, this is furan dicarboxylic acid, and of plant-based monoethylene glycol. And these are the monomers for synthesis of PEF polyethylene furanoate. And as a polymer, it can be implemented into packaging. It can be implemented into textiles, into films. And you can see the size of the market. These are the huge markets, which gives a very nice potential for the implementation of PEF into. So producing a bio-based raw material like PEF and converting into the applications is not just enough to create a sustainable bird, and we have to find a circular way to reuse the waste from these applications. And this is also the field we are working on, that how uh, this textile like the products after use collected and then they are recycled, converted into a high value product again. So this is all what we are working with. So you can see the Avantium logo at some places, and this shows that this technology is governed and covered by the Avantium. So we have the technology to convert the agricultural and the forestry waste into sugars, and conversion of sugars to FDCA and plant MEG is also covered by Avantium fully. And we are covering the technology in uh, in the process to PEF. Thereafter, definitely it is not possible that we can convert the PEF to all kind of applications, and we are working together with a huge range of partners whom together we are working with to convert PEF into packaging stuffs like bottles and so on, textiles and films. So this is our portfolio we are working with. And if you would like to be interested that where we are from the upscaling or the production point of view, that we have already proven the technology at the lab scale fully. You can see in the lower part of the slide. And then both the technologies FDCA and plant MEG are already working very well at the pilot scale. Now we are moving ahead to convert or to upscale the FDCA production to the flagship scale. Flagship scale means we are building a plant which is close to be mechanically finished now, and the scale of production is 5,000 tons per year. And this is a good plant to show the industrial potential of the production of FDC. And this is the first of this kind of plant worldwide. And by constructing and running this plant, Avantium can show that FDCA can be produced at the industrial scale, like at the lowest industrial scale, and later on it can be converted to the full industrial scale. So going to the next slide, then the next question can be why we are talking about sometimes about PET when we are talking about PEF. So there are two reasons. One reason is that if we look at the plastic industry, the majority of the plastic industry is governed by PET. And the second reason is that the chemical structure and the physical properties of PEF are quite similar to PET. Therefore, a short comparison makes quite sense. If we look at fossil-based PET, which is produced from monoethylene glycol and terephthalic acid, PTA, then it is 100% fossil-based PET or the plastic. Currently, they are also already implemented approach of making the PET partially bio-based. That means the plant waste or the bio-based monoethylene glycol is used together with terephthalic acid to make a 30% bio-based PET. But is it enough? We think no. That's why our approach is to make 100% bio-based plastic or polymer, which is also a polyester and equivalent and having equivalent properties and processability to PET, which is PEF. There we are using 100% bio-based plant-based MEG, and also plant-based FDCA, and thus making 100% bio-based polyester, which is PEF. So after looking saw difference, then we can go into little bit more detail that what the difference is at the polymer level between PEF and PET. So here we can see the difference that monoethylene glycol group make the same chemistry as in case of PET, but based on the difference in the between FDCA and terephthalic acid, there is a difference in the ring structure in the middle. Here you can see that instead of 6 carbon ring, there is a 4 carbon ring along with 1 oxygen atom. So there is a 5 atom ring. And if we compare these two rings, then in case of PET, we can see that benzene ring or the 6 carbon atom ring is very much similar, and it can flip around, which gives the nanoscale rotations, and also the possibility of flexibility here. But in case of the PEF, this furan ring is not as symmetric as the benzene ring, and therefore the rotational frequency is very much restricted. And due to the oxygen atom available in the furan ring is also more polar than the PET. So these are the differences. The one difference which is mentioned in the left part, that the repeating unit of PEF is also shorter than PET. So these are the three basic differences, and why we are talking about it, because later on these differences will be interconnected and correlated with the properties of the polymer. So therefore, it is important to understand what are the basic differences at the chemical level and what kind of differences it can produce in the processability in the textile industry, or in the textile processability, or on the rheological properties. So let's go ahead, but we should keep these differences in the mind. And then a very short overview that where the PEF has already been implemented and what are the value propositions. So if we look at in the packaging section, that PEF has a much better O2 like oxygen and carbon dioxide barrier properties, even though it is processed in the existing PET lines in the similar process and so on, and we can get the better properties. So for the packaging, it is quite important that how the barrier properties are. So PEF has 10 times better oxygen barrier properties, and also much better water vapor properties, and 16 to 20 times carbon dioxide barrier properties. If we look at the mechanical properties of PET of PEF in packaging applications, then it has higher modulus and strength. We have also worked a lot on the fiber development, and we can see that PEF can be processed in the similar existing equipments as PET has been produced. And due to the lower melting point, it can be processed at the lower temperatures than PET. So there we see the advantage of low energy consumption and so on. So these are the basic differences if we compare, and if we talk about the value proposition of PEF over PET. So before going into the application, I would like to give some overview of the physics which is impacting the processing behavior of PEF. So in the previous slide, we talked about the slight differences between PEF and PET, and here we will show how the PEF is what kind of effects are prominent in case of PEF, so that we can fine tune the processing of PEF in the product development. So, but first the question comes, why do we need to go into detail? Is it really necessary to look at the rheological properties, at the impact of the shear, at the impact of the temperature, and so on? So let's have a look how the textiles are produced from a polymer. And textiles is a very broad area, really very broad, that the different kind of fiber-based products are made. So generally we think that only the clothing are the textile, but it is not. If we sit in our living room and look around, then first of all, not only the clothing, but we will see that we are sitting on the sofa, which is also made of textile. Then we will see that there are also some wall hanging, which is also made of some textile canvas. Then we look inside the wallpaper on the walls. They may also be made of non-woven textiles. Then if we look inside a building, there can be textile reinforcements. Then we can look on the book which is on the sofa table. Then it can also have some textile fabric in the casing of the book. So there is textile all around. And even if we go into the detail, and if there are some more composite structures, maybe in the sofa, maybe in the bed, maybe in the somewhere in any kind of furniture, then these composite structures are also made of fiber reinforcement into plastics. So it's a lot. So we cannot go into the detail of everything, but I take an example of an apparel, and then we see how the apparels are produced from the polymer. So we take the polymer and go through the melt spinning process to produce partially oriented yarn, which is called PO-by. And the meaning of PO-by is that the polymer is converted into the yarn without having high level of orientation. So it is little bit technical detail. Orientation means it is not stressed a lot to make the yarn more stronger, so that it can be again processed to make the textured yarn or plied yarn if we want to make it thicker. Textured yarn is used to give some kind of texture. Texture means the fluffiness and the softness to the yarn. And then to make it more thermally stable. Thermally stable means that when we are wearing a t-shirt of size 46 or 42, then after first washing process, it should not shrink to 41 or 39. Therefore, we need the steaming and the heat setting, and which is called the steaming of the yarn. Then it is dyed to give some color effect. Then it is woven or knitted, whichever is necessary. Then there is also some finishing processes, and then the fabric is made. And this fabric is still converted into the clothing or the apparel. So this is a very common process. There can be something less or more depending on the properties required. And my focus is here on conversion of polymer to PO by yarn. So what is the concept of melt spinning? Concept of melt spinning is to to give the input factors like heat and shear in the melt spinning machine. And under the influence of heat and shear, the polymer is converted from solid granules to melt like a liquid, very thick liquid like a honey. So honey, we know how consistent the honey is. So it looks like similar, but at this high temperature. And then this melt is deformed or converted into the filaments form. Those who are not familiar with the filaments, this terminology, filaments are like, I think everyone has seen the spaghetti machine where we take the dough of flour and then we convert into the fine threads. So filaments are like spaghetti, but they are much finer, more or less more than 100 times finer than the spaghetti. And then these filaments are gone through the longitudinal stress application. Longitudinal stretch means like stretching the filaments a lot, so that the polymer chains inside the filaments are oriented to get the good mechanical properties. So now if we summarize all the input parameters, heat, shear, deformation, stress application, we have to study all these before going to set up a process. And how do we study it? This is study by making the rheological analysis of a polymer. During the rheological analysis, we also apply heat, we also apply shear, we also apply different kind of strain and stress, and then we see how the polymer is behaving. So before going into the details of the process, so we will have a look on the rheological studies of PEF polymer. So there are some technical things which are very important. So let's try to understand. But if there is any difficulty in understanding something, then we can discuss again during the Q&A session. So I would like to highlight some terms here, like the reptation time. Reptation time is like, in the simple words, it is how fast a polymer chain can be mobilized by a application of heat and shear. And lower the reptation time is, it is easier and faster to move or to mobilize the polymer chain under the application of the heat and shear. And PEF has a shorter reptation time in comparison to the standard we compare with the PET, because of the lower chain entanglement density. So this is the summary. And how it is calculated, like there is a slope calculated on the rheologic curves, and the slope, if we compare the slope between PET and PEF at any specific viscosity, then we see at what shear rate this viscosity is reached, and the inverse of this shear rate is actually the reptation time. So in case of PEF, the shear rate is higher at a specific at the same viscosity level, and the inverse means if the shear rate is higher, then the reptation time is lower. And this is actually what we want to understand. And what is the use and the implementation of this reptation time? So we understood PEF has a lower reptation time. So if we will apply some heat or the shear, then it should mobilize faster. It means the polymer chain of the PEF. And if it is mobilized the polymer chains faster, that means the change in the viscosity will be faster than PET, which we see also in the curves. That the distance between the different rheology curves is higher than in case of the PET. That with the implementation of the temperature, the viscosity, or the increasing the temperature, the viscosity goes down faster than PET. That means, what is the impact in the processing in the textiles, like in the fiber making? That means if this is a steeper slope in the shear thinning, then it is possible to get the higher orientation in case of the PEF than PET, and this orientation is directly connected to the mechanical properties. Mechanical properties means the tenacity, the modulus, and so on. So starting from the basics of PEF rheology, reptation time, and lower chain entanglement density, and then shear thinning behavior, then we understood that how we can use this phenomena in getting the better properties in fibers and in textiles. Then we look also that how it can be practically implemented. Because of this phenomena which we studied on the previous slides, then we can see that due to lower chain entanglement density of PEF, PEF can be drawn more than PET. So you can see in the curve that the green curve is for PEF and the red one is for the PET. So if we see that where the crystallization, the strain induced crystallization, or we all other words we say strain hardening starts, it starts under similar condition after longer at the higher strain in comparison to PET. That means PEF allows more or higher draw rates or drawing in comparison to PET before the strain hardening starts, which is related to again to the high orientation level of the polymer chains, and which can result into better mechanical properties than PET. So if we look then, like again, going back to the high orientation, that what is the impact? Like these all things are interconnected with each other, that strain hardening is connected with the strain induced crystallization. So why this PEF starts uh, strain hardening later than PET? So there are some interconnections, that in case of PEF, the crystalline organization is different than PET. So it is not yet fully concluded. There are still some debates ongoing, that what is the exact differentiation between the thermally induced crystals and the strain induced crystals. But it is very much clear that PEF does not make any mesophase. Mesophase means uh, nucleation induced by the thermal crystallization, and then continuous crystallization takes place. This is not the case for PEF, but there is sudden transition into stress induced crystallization for PEF. So uh, so that we do not be more confused, please have a look on uh, uh, these data on the right side, that this cycles from the WXT analysis, the X-ray and diffraction analysis, that when the PEF is not stressed, it is complete hollow. Then it is stressed up to some level, it is still hollow, but instantly there is some intensity diverted towards the equators. That means there is no stepwise transition from the hollow phase to the oriented phase and oriented crystals phase, and it is just sudden transition from at some point of uh, uh, orientation and the stretching, and then it remains same. It becomes more oriented. More oriented means intensity is again more and more diverted towards the equators. But this change from, for example, here we can see from the draw ratio of 1.2 to 1.75 is quite significant, that there is no mesophase and it is directly converting into the crystalline phase. So what is the advantage? The advantage is that when such kind of crystallization happens, then the crystals are much cleaner. That means there are less defects inside the crystals, and which gives are more clean crystalline phases. So uh, now if we look at the impact of these all effects, then how we can summarize and correlate the impact with the processability and the product properties. So in case of PEF, there is less rigid amorphous fractions, because as I mentioned that the crystals are very much clean. So there is less interaction between the crystalline and the amorphous phases, and therefore the amorphous regions is less rigid, which helps in the in on the impact on the glass transition temperature. So the rigid amorphous fractions are known to increase the glass transition temperature as main chain segmental motions, which is hindered here. And the glass transition of PEF does still increase upon the stretching, because as that there is no there is very clean amorphous region. So when the filaments or the polymer chains are again drawn, then the glass transition temperature, like the amorphous region, is more oriented again, and the glass transition temperature can be increased. But this is but we have to also always keep in mind that this is the theoretical things, that we know these impacts are very much prominent, but always there is a combination of drawing and annealing and heat setting, which decides what will be the final values of the transition temperature. In case of textile processing, there is one very important property along with the mechanical properties, like uh, if we look at the primary evaluation of the yarns and fibers, we measure the count, we measure the tenacity, elongation, and at the end the shrinkage. Because shrinkage, as I also mentioned in the beginning, that if we make a form, like a textile or a t-shirt, it should retain its size. So this is a big difference that because the amorphous region is very clean and there is no mesophase which can control the amorphous region. So shrinkage behavior is very much prominent, and also it is also dependent on the whole structure, that how is the final interaction between the amorphous and the crystalline phase. But due to clean amorphous region and clean crystalline region, it is necessary to arrange the morphology in a way that the shrinkage can be brought to the required level. So all this morphological history and the information is influencing the mechanical property and also the shrinkage property that we will see in the coming slides. But at the end, we know that based on this know-how, we can get the better properties, which we have already proven in case of the packaging. So after going into the physics details, then we can see the influence on the processing behavior. Like it is about the correlating the basics of the PEF polymer with the processing behavior. So processing behavior, if we look at the melt spinning perspective, then it is more about the stretchability, like the draw ratio at different temperatures, draw ratio at different level of drawing, and the shear. So here we can there is some data that how the temperature and the strain is affecting the stress. So for those who are not from the textile and the polymer background, I'm using different terms like elongation and strain, which are very similar to each other. There is only some difference of the interpretation. Similarly, the strain, stress, and the tenacity are also the similar terms, but based on the calculation way of calculation, it is defined. It is different names are given. So we can compare, like the stress is similar to tenacity and strain is similar to the elongation. So if we see the impact of the temperature and the impact of the shear, then we can see how the polymer is behaving. So in the previous slides, we learned that the reptation time of the PEF is much shorter. That means if the polymer, the temperature is applied, then definitely due to the reptation behavior, the strain will increase. And if the shear is applied and due to the lower reptation time, then a faster orientation can be achieved. And due to this faster orientation, the strain hardening starts. And that we can see here. For example, I compare two curves. One is in the orange color, one is in the green color. In the orange and the green, in the solid lines, we see the difference in the temperature 90 degrees centigrade, 96 and 101. And if we see the curves of solid orange line and solid green line, then at the higher temperature at 101, the true strain is increased and the strain hardening starts later. So this is the impact of the temperature, that due to the temperature and the shorter reptation time, the mobility is increased and the strain uh, and the hardening starts later. But if we compare the same temperature but different level of shear rate, then there we take the example of solid line of blue and the dotted line of green. Then same temperature 109 degrees centigrade, and the blue one has solid blue line has the higher shear rate. So if we compare these lines, then we can see that the solid blue lines, there the strain is longer, strain is higher than in case of the green dotted one. So by comparing these data, then at the higher shear rate, then again the chain mobility is higher, and therefore due to this chain mobility, the one side the mobility is higher, but on the other side, due to low repetition time, the orientation can be achieved much faster, and therefore the strain hardening also starts sooner. So these are the effects that we have to correlate with the melt spinning process, that when we decide for different kind of spin pack hole diameter and the different L to D ratio, then how much shear rate can be imparted, and what kind of nucleation or the strain induced crystallization we can expect, and how the filament property will be resulting thereof. So these information are always necessary to keep in mind when setting up for the melt spinning process. So if we will go in the detail, it will take a very long time of the individual curves, but I just wanted to give some overview that how the temperature and the shear rate can affect the properties. If there are any questions, definitely we can talk in the Q&A session. So there is again some more data which is important, because when we talk about the polymer, then polymer behavior, then it is very much dependent on the molecular weight. So higher the molecular weight means the entanglement per chain will be increasing, and therefore the natural draw ratio will be lower. But there is one another study where we have already realized that to get the similar melt flow behavior, then the PEF has to have higher molecular weight than PET. But the impact of the molecular weight on the natural rate is shown on the right side curve. And additionally, we have also studied that the moisture content can also impact the stress strain behavior, because water molecules from the moistures are uh, are having the effect of plasticizing on the PEF, and therefore this effect also need to be considered while the processing. And plasticizing effect means higher strain under the same loading. So now coming out from the basic studies, then we can see what kind of textile development we have done based on this know-how. So we started with some basic studies where we produced some polymer of different IVs and saw what kind of spinability it can have. And the spinning trials were focused to see what is the behavior if we use different spinning speeds. So we were focused around all possible binding speeds from 1000 to 6000 meter per minute, which are which is a range which is used in the industrial production. Then we can see by changing the spinning the take-up velocity and changing the IV, how the stress is increasing. So in the first curve, you can see that if we use one IV but different take-up velocities, then the stress continuously increases. And with the higher IV, we can even get the high stress value. Stress means the tenacity value. And this is also valid for the modulus. One very important phenomena we have seen uh, uh, while measuring the filament diameter with the distance from a spin pack, that there are some specific distance where we can see the neck forming behavior, and neck forming behavior is directly related to the strain induced crystallization. So there are some specific speeds, mainly above 4000, and in some, depending on the IV, it can be 4000 and 5000. And at this speed, we can get the neck forming and the strain induced crystallization in the filaments. Here you can see that how the WAXT pattern is changing if we are increasing the speeds. So at the lower speeds, 1000 and 2000 meter per minute, there is mainly the amorphous hollow. But if we increase the speed, then we at the lower IV means here 0.8. then intensity slightly moving towards the equators. But in case of IV 1.05 that we learned in the basics, that at the higher IV, the chain interactions are higher, and therefore the mobility is hindered, and the faster crystallization can start. And here we can see that the due to the crystallization around 4,000 meter per minute, the intensity is quite well moving towards the equators, and which becomes very prominent at the higher spinning speed. So there is a comparison with some fully drawn and annealed. By using the drawing on the goddets and annealing, we can get a complete shifting of the intensity towards the equator. That means PEF can get the very well oriented structure. So after having this all basic studies, an overview that what has already been developed from the PEF, in the last years, there is one PhD thesis on PEF based textiles. So there was successful development of yarns and texturing processes, and also demonstrators like shown in the t-shirt form from the PEF. And the first study has shown that it is possible. It is already quite old, but it is possible to make the yarns and textiles from the PEF. And it is already a dyed yarn or dyed fabric. Therefore, the dyeability is also already been proven. Then, after all these basic studies, then we started industrial scale development. And here we took the industrial scale process as a benchmark. So if we look at the PO spinning, which is taking place between 2,700 and 3,400 meter per minute. So around 3,000 per minute is a standard process, which we developed for the PEF. And we made different kind of yarns with different number of filaments and counts. And this yarn was actually the POY without having any high level of drawing. So all yarn and process development took place in the existing PET equipment. So it is all very well proven that we do not need any optimization in the instrument, in the machines. And PEF was processed at lower temperature than PET. That means there is a huge potential of energy saving in melt spinning process. These yarns were textured. Textured means, as I mentioned, that to insert some bulk and to improve the comfort properties of the yarns. So there we also did several basic studies by changing the heater type, the length of the heater, temperature, draw ratio, winder ratio, and so on. And we have a lot of data based on this, and we have chosen the best process parameters and developed the yarn for the industrial uses. And you can see a range of the type of yarns we have developed, which are currently in the implementation in the textiles. Similar thing we did with monofilament also. We have done the monofilament melt spinning process development, and which was very successful. And upscaling and optimization and so on is ongoing, and we are looking for a range of applications based on the monofilaments. There were trials to develop the PEF based staple fibers, and you can see that we have successfully made the crimped staple fibers. And then at the lab scale, we have proven the non-woven possibilities based on the PEF fibers, and then by the needle punching, we have made successful non-woven fabric. So we have covered a range of the application and the processes so that PEF can be used in a variety of textile applications. It is also very important to see how for the aesthetic and the visual impression, that how the PEF can be dyed. So you can see that PEF dyeing trials has been made for different colors, and this is all done in the existing machines without developing any any big optimization in the dyeing process or in the equipments. So it is possible to use the existing infrastructures and to get the good effects and the good dyeability. And we are working on improving this further and to industrialize the dyeing process and also the yarn development processes, and looking forward to the additional value by using PEF, for example, different temperatures and so on, so that how the PEF can provide better performance and better value in comparison to PET. So we have developed a lot. We are already on the route of the commercialization and working continuously on making it better. Thanks a lot.